minute, then we can start.
Okay.
I guess Devasis has started the recording. Yeah, so you can start now.
Okay, sir. So hi everyone, I am Aditya Jain. I am from Group 8 Kachra Set. So today I am going to present the paper titled Every Walk's a Hit, Making Page Walks Single Access Cache Hits. So let us first see what is the problem. We all know that nowadays the applications which we are running are mainly in a data in a high data driven. So such large data applications suffers from frequent page table walks. So we know that they are currently we use 4 or 5 level page tables. So if there are 4 levels, then in the non-virtualized environment, we need to perform 4 accesses to the main memory in case of page table walk. And if it is a virtualized environment, then we need to perform around 24 accesses. This we will see in the later slides how it will and how 24 accesses are required. And this problem becomes more difficult when there is trashing. So before going to the solutions proposed in the paper, let us go through some backgrounds. So the page walks are generally cached in 3 ways. In the TLBs, in the data cache, and the page walk cache. We all know about how it is cached in TLBs and data cache. So we will discuss about the page walk caches. So this is about how it happens in the page walk caches at a 10K feet view. What happens is suppose we get an address translation request from the processor. If the first 9 bits matches, then we don't need to go to the L4 and a page table level. We can directly go to the L3 levels. So we are able to save one access in a single access. If the first 18 bits matches, then we can directly go to the L2 level and we are able to save 2 accesses. If the first 27 bits matches, then we can directly go to the L1 level. So we are able to save 3 accesses. So we will now need to perform just one access for the page walk.
Hey, when you say matches with what?
So the entries in the table means this is like a cache only. It will contain 9 bits. There are 3 levels. One is L4, L3, and L2. So the L4 level contains 9 bits.
No, it doesn't contain 9 bit. It has entries that
Yeah.
stores one of the intermediate levels, or maybe one of the levels to make it precise.
Yes, sir.
So then can you explain?
So if this 9 bits matches with the means with the MSB 9 bits of that logical address, then we are able to skip the L4 level.
Okay.
So are you meaning to say that you are storing some particular one combination of 9 bits there?
Yeah, this page walk cache is already present in the Intel and AMD processor. I think
Yeah,
ARM
so
processors.
they have
Yeah.
one particular 9-bit combination for L4 and one particular 18-bit combination and one particular 27-bit combination. Is that what you are trying to say?
Not one. There are means several lines. In the L4,
So
there
then
are around there are 4 or 5 lines. The matching is performed parallelly.
No, matching is performed parallelly, but what Varun was asking, you didn't answer. You will compare all this L3, L2, L4, whatever, how many intermediate page walk cache you have, that you will probe concurrently to save latency. That is okay. But
Yes,
what
sir.
about the internals of each of this PWC?
So the L4 will have 9-bit entries, which when match, and then we can directly go to the L3 level.
So then how it is different from accessing the L4 given below?
How it is different? This L4 is of the page walk cache. Means there are 3 levels in the page walk cache. It is labeled as L4. In the paper, it is labeled as L4.
Where is this page walk cache present in the hierarchy?
It is present before the data and data cache.
Okay.
If there is a miss, then we have to go to the data cache.
Okay. Okay. So this is similar to Biswa. This is similar to page structure caches, is it?
Yeah, they are different
Yeah,
names. MMU cache, page structure cache, page walk cache. Yeah, they are all same.
Okay. 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 Okay.
So should I proceed?
Yeah.
So why this problem is a big deal is because in virtualization we have already seen that there will be 24 accesses required, because there we need to perform a 2D walk. We will see in the next slide how this 2D walk is done. With PWC caches, this 24 accesses is reduced to 4.4 accesses on average. So this is the diagram of how 2D walks works. The task for us is to get map the guest virtual address to host physical address. So to access the data given here, we need to get this GL4, GL3, GL2, and GL1. For this, we need to perform and we have to access all these four levels of the host. So total there are 24 accesses required.
Why 24?
For getting GL4, we need to perform 4 accesses in the host level, and then we have to perform access the guest level 4. Then to get GL3, we have to perform again 4 accesses. So in each of the first 4 lines, we have to perform 5 accesses, means 5 into 420. And in the last level, we have to perform these 4 accesses. So 24 accesses are required in the naive approach, but with the PWC, this is reduced to 4.4 accesses on average. So the solution which is proposed in this paper is they have 2 goals in mind. First one is to reduce the number of accesses for page walk. For that, they are using page table flattening. And the second one is to reduce the latency for each access. For that, they are performing cache prioritization. As we can see from the diagram below, with flattened and the number of accesses is reduced, the dark blue part, and because of cache prioritization, the latency is reduced. And as of in some cases, it is also found that the DRAM and since the DRAM accesses are reduced, so the energy is also reduced, energy requirement. So let us see what page table and flattening is actually. So in this, what happens is we merge 2 level of 4 KB page table nodes into a single 2 MB node. So what happens is the number of levels is reduced. We will see in the next slide the animation how this works. And for this, we don't need to make any big hardware changes because 2 MB page support is already present in current and hardware and operating systems. So this is how page table flattening works. First, we will see how in a conventional 4K page table works. This I think everybody has seen how it works. First, we get the base address of L4 from the CR3. Then we go to the L3 level, then to the L2 level, then to the L1 level, and finally we are able to access the frame number. So here we can see that there are 4 accesses required in the naive manner. In page level flattening, we merge the first 2 levels L4 and L3 and the level L2 and L1. So now instead of 9 bits, we have 18 bits for referencing the page number. So the number of levels here is reduced to 2. So only 2 accesses are required. This is how the virtualization work in flattened 2D walks. Earlier we have seen that there were 24 accesses required, but now with flattening we require only 8 accesses. So next, let us see what are the benefits of flattening. What they have done is if the fork they have they have provided features. If the 4 KB we are not able to allocate 4 KB, if we are not able to allocate 2 MB, then then their work changes to 4 KB pages. And flattening plus PWC has reduced the accesses from 4 to 1.
Hey, hang on. Go back to
Yes,
previous
sir.
slide.
Yes, sir.
Oh, the PWC is already there. It's a known concept, right? It's not the contribution of the paper. Flattening
Yes,
is
sir.
the contribution.
Yes, sir. With PWC, the access is reduced from 4 to around 1.5. With flattening, it is reduced to 1.
No, hang on. So PWC itself is a technique that tries to reduce the page table walks, right?
Yes, sir.
In isolation. Now,
Yes,
I
sir.
think your comment or observation is if you use flattening along with the page walk cache, it's even better.
Yes, sir.
Mhm.
So next we will
So,
see the
I have
second.
another question. Go back.
Yes,
Yeah.
sir.
So even current machines, they have page size up to GB, right? 1 GB. So why not go for just one level or maybe why 18 bits, right? Why not push it till 1 GB?
Sir, 1 GB means 27 bits, right?
Yep.
For
1 GB meaning 30 bits, right?
yeah, 30 bits. Sir, they have mentioned it about they have mentioned somewhere in the paper that they have not performed work on that, but it is for future work. We can go for that.
Could you comment why?
Sir, I don't know why they have not performed, but they are saying that we can merge the L5, L4, and L3 level to get a 1 GB page.
Okay.
So next is cache.
Actually, I have a question. Is the page table hierarchy against the means? Are we not losing out on page table hierarchy by flattening the whole page table? What?
Yeah, there are some issues like bloating and all, means page fragmentations is increasing. But the main aim of this paper is to is for large data-driven applications.
Sorry, can you repeat the last part?
The main focus of this paper is for large data applications.
Okay.
Okay, so next is the cache prioritization. So cache prioritization is based on two observations. First one is that page table size is almost equal to the LLC size, and the second one is that TLB miss rates is strongly correlated to data miss rates. So what they have done is they have biased the cache replacement policy. What is mean by biasing is that during period of high TLB miss rates, they prioritize page table entry over data, which means that the data is removed is evicted first before evicting page table entry in case of replacement. So the hardware changes required for this is minimal. Uh, First, we need to we have to augment this page table walker, because earlier we have used to have 9 bits for this, but in this case we have seen that there are 18 bits required. So we have to make changes for that. Then second one is that in some cases we can have 4 KB pages, and in other cases we can have 2 MB pages. So the operating system needs to know that what is the size of the page in the next level. So for that we require 1 bit. Then for performing the cache prioritization, we have seen that we have to evict the data first before evicting that page table entry. So for that we need some extra bits to distinguish which entry is a actual data entry, or is it is a page table entry. So the heuristic they have used is 99% of the time they evict data over page table entry, and if there is no data, or in the remaining 1% time, they are evicting the LRU entry. So
Aditya,
this is the
Aditya, just a question in the previous slide. Since the x86 already supports dynamic page sizes, right? 4 KB, 2 MB, and 1 GB, do you actually need this 1 bit and all? Because OS has this information, they already have this infrastructure. Do you think you actually require all these hardware changes? Other than the
actually,
change in replacement policy that I do agree, because you are prioritizing a page table entry. But other than that, do you think you require all these changes?
We can make use of unused bits, which is already present there. If there are no unused bits, then we need to have one extra bit.
So probably you don't require hardware changes, right? The bits are already available. That's what I wanted to check.
Yeah.
Yeah,
And we can also
but
have
for cache replacement, you need it, right?
for cache replacement. Yes,
yeah,
sir, for
but
cache replacement.
Cache
for
replacement,
this,
you might need Biswa, but my thing is, cache has nothing to do with whether it's a 4 KB
Yeah,
page
yeah,
or a 2 MB page.
Yeah. It's just a PT. That's what.
Yeah, that's it.
Yeah. So should I move forward?
Yep.
These are the results from the paper. The takeaway one is from the first image. We can see that with page table flattening and with PWCs, there is only single access required for page walk in all workloads. This dark blue line part. And the takeaway two is from the second graph, with when prioritization is combined with the flattened page table and PWC, the latency is reduced, which can be seen from the green bar at the bottom. So latency is reduced from 50.9 cycles to 29.1 cycles per walk. So this is the result in the non-virtualized environment which we have seen earlier. In the traditional page table walk, we require 4 accesses. With PWC, this is brought down to 1.5 accesses. With PWC plus flattening, this comes down to 1 access. And when we add cache prioritization, it takes 1 accesses, but in most cases we find the data in the cache only with cache hit. And
yeah, I have a question here. So when they evaluate, the baseline has PWC or it doesn't have?
Yes, sir, they had.
Okay. So then basically it's a improvement from 1.5 to 1.
Yes, sir.
Okay. So this 50.9 is actually for 1.5, is it?
No,
50.9 is for traditional Biswa. He showed it in the previous slide.
Yeah, traditional has PWCs.
Traditional has PWC, then what is different between 4 and 1.5?
No. We should not confuse. This is per walk. My question was, when you are finding out the cycle numbers, so the baseline itself has PWC. Is that right?
Yes, sir.
Then what is the number when you don't have PWC? That number is around 200, 300, or what exactly it is?
That I think is not mentioned in the paper.
But you are sure that the baseline is with the PWC, right?
Yes, sir.
Okay.
So this is the result in the case of virtualized environment. In the naive approach, we require 24 accesses. With PWCs, this is brought down to 4.4. And with PWCs plus flattening plus, actually it is not mentioned in the paper that whether this 2.8 comes from cache prioritization as well or not. So it is mentioned that it is 2.8 in PWCs plus flattening. So the final conclusion is that page flattening and cache prioritization has reduced the number of accesses and the latency for each access. There has been 14% performance gain. In non-virtualized environment, we require 1 access for page walk, and in the virtualized environment, we need 2.8 accesses instead of 24. So thank you. Any questions?
Yeah, questions?
Aditya,
anyone? Yeah, go on.
In trying to protect any page table entry in the cache, is there a possibility that you increase the number of DRAM accesses for data blocks?
DRAM accesses for data blocks.
Yeah, you have definitely reduced the number of DRAM accesses for bringing a page table entry. No denial about that. But in trying to protect a page table entry, you might have increase in misreads for data accesses, right? Not translation accesses, for data accesses.
Yeah, misreads increases for data.
Yeah, so how much was that? Means I couldn't see any analysis I probably didn't read the paper also thoroughly, the results part. So I just wanted to know, have they shown anything in regards to the
Yeah,
trade-offs?
they have mentioned somewhere that around 5% improvement was there with
Improvement or
data.
degradation?
That in for data that there has been degradation around 5%, and with and for that for accessing the page table entry there has been improvement. So the overall improvement was around 14%.
No, hang on. So what Barun is asking is there a negative interaction because of your proposal or the author's proposal? So if you are saying that the net gain is now 14%, so if we remove the negative interaction, that will become 19%. Is that correct?
No, sir, not 19%.
You
So I
got
have
the
to,
question right? What exactly Barun asked?
yes, sir.
So you are asking
Sir,
like you are reducing the page walk latency, but in the process of improving page walk latency, is it possible to increase the data load latency, the usual load request that you will send to DRAM?
yes, sir. Because of cache prioritization, we will first await the data instead of page table entry.
That's
So the
what he was
data,
asking.
yeah. So data will not be there mostly. So because of that, data rate is means improving, but because of page table entry, the overall performance is improving.
That I got it. So in their evaluation, is it a multi-core evaluation or it's a single core?
So mostly single core evaluation, but there has been one section for multi-core. I don't have the graphs. If you want, I can show in the paper.
No, it's okay. It's okay. Because what Barun is asking is just pretty intuitive. There will be cases where this particular trend will happen.
Yeah, and
Yes.
if in case, like he said, by protecting the page table entries, if we are going to get so much benefits, and if we can compromise a bit on evicting the data cache blocks, then why don't we look at LLC replacement policies that take care of the page table entries first, and then take care of the data caches? Why
That's what this
hasn't been
paper is
this?
doing, right? That's what this paper is doing.
Hmm.
So the paper is saying
Yes.
people are not doing it. We are doing it now.
Yes. Yes.
But there are still there will be hiccups depending on especially in multi-core. In single core you may get away with it.
Yeah.
Yes, yeah.
Uh,
So it may happen that you will see performance degradation. Forget about improvement. I'll give you a simple example. Maybe if you have pen and paper, you can calculate. So do they mention anything about the working set of these applications? Data set size, footprint, anything?
No, sir. They have mentioned about the benchmarks.
Wait. So what is the
Yes, sir.
data set size? How much memory it requires?
Sir, they have.
Sir, they compare it with the 8 GB data.
Yeah,
Yeah.
8 GB.
Is the working set of all these applications is 8 GB? Is it?
So they
I'm
have
asking
mentioned.
to run this application or to run this benchmark, how many pages you need. So usually you will come up with the notion of working set or footprint or data set size, right?
Yes, sir. They have not mentioned that.
I guess that should be there somewhere. Do they mention anything about the benchmarks they use? Why they pick
Yes,
these
sir.
benchmarks?
Yes, sir. These are all the benchmarks.
No, do they say why they pick this?
Uh, they said that these are means some of the benchmarks have means many accesses.
Many
In
accesses
this
is
section
okay.
means
Biswa,
large
from
number.
the kind of applications that I'm able to see, the applications are more like those applications which have very irregular access patterns, like certain
I
are
got
getting
it.
Yeah.
Got it. Got
Yeah,
it.
Yes.
so when LLC is more or less behaving like a streaming kind of stuff, then protecting the page entries might give us more benefits intuitively.
Sir, here they have
Yeah, but
mentioned that 8 GB is they have run GUPS on 8 GB.
okay. And then spec will be around 1 GB, 2 GB kind of depending on the footprint.
Yeah, that is not mentioned. Only GUPS is mentioned.
Okay. Okay. Yeah, Varun, what you are concluding is one side of story, right? So what if I'm running my all these memory intensive applications along with just cache fitting applications, or just above cache fitting?
Okay.
Yes, sir,
So
they have also mentioned this LDBC 6.6 GB.
okay, yeah, I got it. Okay, okay. So okay, you can do a pen and paper calculation, right? So let's make it simple, like power of 2. If you are demanding 4 GB of memory, right? If you have
Yes.
4 KB page size, you will need 1 million entries, correct? 1 million page
Yes,
table
sir.
entries, right?
Yes, sir.
One page table entry is 8 byte.
Yes, sir.
So it is 8 MB.
Yes, sir.
So now you are saying that I will store this 8 MB of PTE for 99% of the time.
Sir, not all, means not totally. It is
Theoretically,
yeah, yeah,
because I'm not
theoretically.
doing experiments now, right? I'm just thinking at a high level. So I'm just trying to correlate what Barun asked and what can happen, right?
Yes,
So
sir.
so take a simple example, right? 4-core system with 2 MB per core, so that is 8 MB, right?
Yes, sir.
And let's say you are running 4 such applications, so that means they will demand around 20 MB for only PTE, right?
Yes, sir.
And then there is data. Along with the PTs, you have the data also, right?
Yes, yes,
So
sir.
I think this 99%, 1% is kind of heavily skewed. It should be highly dynamic depending on the dynamics of the sets. Now, not
Yes, sir.
a generic number, but this is okay for a single core experiment where you are not running or you don't have co-running applications that have mixed behavior. That's why it's kind of okay. But it will have its own issues. Barun,
Yes, sir.
does that make sense?
Yes, but there is another observation, Vishwa, in caches which say that you have a huge amount of presence of dead blocks.
That's there. I'm not ignoring it. But so let's assume that you have dead blocks for like 60 to 70% of the time. Okay.
Yeah,
So now with this 99% rule, you are not hampering the 70% of the data blocks.
absolutely, yes.
Yeah, but you are still hampering the 20% of the data blocks.
Possibly, yes. But then if the trade-offs of the page table misses are so high, then maybe the benefits that they are
It
saying might
depends.
still stand. Yeah,
It depends. So that's what I'm saying. It with the multi-core system, it may not hold true all the time.
absolutely, absolutely. Agreed, agreed. Yeah.
For single core, it may be just okay to say that okay 99% of the time, but multi-core, you need more maybe bit of dynamism or bit of more fine-grained approach.
Or some feedback kind of a system which suggests that
Maybe,
okay, it should
yeah,
not be. Yeah,
yeah, yeah, yeah. Hey, one
thanks,
more
thanks.
question. How many page table walkers they have in their experiments?
So they have, I think they have one only. It is in a written in the paper that. So they have not mentioned actually this. In that they have mentioned this table only.
That's okay. Mentioning a table is okay. Because if I have multiple page table walkers, which is actually there, if you look at the latest Intel machines, you will find more than one page table walkers.
Yes, sir.
So in that case, I can amortize my page walk latency.
Yes, sir.
Concurrently, I can handle multiple or concurrently I can walk the page tables.
Yes, sir.
Did they mention anything about the TLB size? Okay, it's there. Yeah, 32. Okay, yeah, this is good enough. So they change only the last level cache replacement, is it? Not the L2, L1?
Yes, sir. Last level LLC.
Why not L2, L1?
I think so. They have changed both L2 and LLC, not L1.
Okay. Okay. Yeah. Any other questions?
Yeah, I have a question in slide 4. They're saying we are storing multiple entries for L4, L3, L2, right? So what is the overall overhead because of its storage overhead?
1 minute. Page slide 4.
Yes.
What is your question?
Yeah, so here before comparison, you said there we will be storing different entries for L4 level, L3 level, L2 level, and all, right? So what is the total storage overhead because of it?
Yeah, actually PWC is already present in the Intel, and I mean Intel and ARM machines. So it is mentioned in the paper that L4 level has around 4 or 16, around between 4 to 16 and rows.
Not rows, entries, man. Come on.
Yes, sir, entries.
Okay.
So Sai, it is already there in a baseline system. It's not author's idea or their proposal.
Yeah, authors have proposed cache prioritization and flattening.
Right. Yeah.
Okay, sir, got it. So is it 4 to 16 for overall this overall page walk case, or it is only specific for level 4?
I think it was given that 2 levels have 4 in a line, 4 entries, and the one level has 16 entries. I forgot which one has the 16 entries.
It's pretty straightforward, right? If you are using more bits, then you need less number of entries.
Yes, sir.
So if I'm using, let's say, entire 64 bits, then I just need one entry, right?
Yes, sir.
Yeah.
Yes, sir.
So, okay. Any other questions?
Did they mention about the cache hierarchy?
Cache hierarchy. They have L1, L2, and LLC cache.
I mean, is it inclusive, or how actually the entries are filled into the caches? Because you said that both L2 and LLC, they both have. I mean, in both of the caches, the page table entries are prioritized over the data blocks, right?
Yeah.
Yeah. So
Actually, it is not mentioned in the paper whether they are using inclusive cache or exclusive cache.
It is non-inclusive to make it safe. So anyway, inclusive caches are, at least in the current world, it's not that mainstream. So yeah.
okay.
Okay. So are we done, or any other questions? Okay, then looks like we are done. So Devasis, you can stop the recording. And now I need to share my screen. Yeah, the lecture is not